All right, so we're going to start in on chapter 16. This is a little bit shorter of a chapter, but it's very important. It's a concept that we're going to piggyback off of a lot in this course. It's going to come back up over and over again in other chapters, okay? So this is the concept of chemical equilibrium here, all right? So we're going to take a look at a very simple chemical equation. Once my pen works. All right, it turns out that if you take dinitrogen, tetraoxide gas, this will decompose into nitrogen dioxide gas. Okay, so let's practice what we learned from Chem 1A. Everybody take a second and balance this chemical equation here. All right, chemical equations don't do us any good if they're unbalanced. All right, so all I need to do to square this off is to put a 2 on my product side here. Now I got a balanced chemical equation to work with, right? So step one, anytime you see a chemical equation, balance it. It's no good to you if it's unbalanced, okay? So we're gonna make a little graph here. I'm gonna keep track of my reactant in blue and my product in red on this graph, okay? And what we're going to do is we're going to make a plot of concentration versus time. Okay? And I'm going to start this experiment here with only reactant in my flask, right? So I have some reactant and my concentration of product is 0 at like my T equals 0 at the very beginning of this experiment here, right? So at the very start, I have all reactant, no product. Okay? So now we're going to start the clock. We're going to kick this off here. What's going to happen to my concentration of my reactant as this reaction starts to progress? Is it going to go up or is it going to go down? My reactant is going to get consumed, so my reactant concentration will decrease. Okay? And what's going to happen to the concentration of my product after we kick this off? Is it going to go up or down? Up. It's going to go up because product gets produced as this reaction occurs. Okay? Not only that, but because of my balanced chemical equation here, I'm going to get twice as much product that's produced as I have reactant that's consumed, right? Because I have a 2 in my balanced chemical equation. So the height of my red bar here is now twice as big as the height of that blue bar, right? Because of that stoichiometric ratio in my balanced chemical equation. Okay? So reactant gets consumed, concentration goes down, products get produced, concentration goes up. Okay? If we keep this going and we keep on following this along here, we'll see all of a sudden this concentration start to peter off until it hits this plateau. Okay, same thing with my product. My concentration's going to rise, but eventually it's going to get to this point where it plateaus here, right? So at some point in time, the concentration of my reactant and the concentration of my product are no longer changing. They have flatlined. They are remaining constant here, okay? This region right here is what we call equilibrium. Okay, so Some notes that we can make about equilibrium in general. All reactions will proceed until they reach equilibrium. Right? So all reactions are occurring, and they're going to keep on occurring and keep on occurring until they get to this equilibrium region here. Okay, so the direction of all reactions is towards their equilibrium. What's up?
In the graph, the first two initial lines of reactant and product are linear. They are not hyperbolic. Why is it so?
At the very beginning, they are linear, right? It's just because if you're looking at even if you look at a hyperbola and you look in a very narrow region, it's a linear. You can sort of approximate it with a line. So at the very beginning, before these things have petered off, you're right, they do start to curve, but at the very first instant, they are linear. Okay, we'll talk about kinetics, and that might make a little bit more sense then. Okay. The other thing that we want to note about our region here, we said that these graphs will plateau, right? So at equilibrium, the concentration of your reactants and products are constant. All right, that's what it means to be in equilibrium, is things are no longer changing. Okay? And let's look really carefully at this graph here. Notice that my amount of reactant has not gone all the way to 0. At the end of this experiment, once it reaches equilibrium, I still have some reactant left over in this flask. Okay? This is this update that we have to do to the way that we've been looking at chemical reactions compared to Chem 1A. In Chem 1A, we always think about chemical reactions as starting with reactant, and then they get turned into product, and I always get 100% product at the end, right? That's kind of how we've been simplifying looking at chemical reactions. That is a pretty good approximation for a lot of reactions, but strictly speaking is not true. There are plenty of reactions that will reach equilibrium and still have an appreciable amount of reactant left over. Okay? Not all reactions go 100% to completion. All right? So we got to update the way that we think about reactions a little bit. It's not this stuff is always just turning into that stuff. Okay? We could still have some of our reactant left over. So in this case here, again, equilibrium is reached because my concentrations aren't changing. I have a bunch of product in there, but I still have some reactant left over as well. Okay? All right, and then the last thing that we're going to note about equilibrium here is that at equilibrium, the rate of the forward reaction is the same, equals the rate of the reverse reaction. Okay, so what the heck do I mean by that? Again, let's look at our chemical equation here. Again, we kind of got to update our way of looking at chemical reactions compared to how we were looking at them in Chem 1A. In Chem 1A, we sort of look at reactions as always going in one direction here, right? Well, when this thing reaches equilibrium, it's not like all the molecules in that flask get together and they're like, all right, guys, we put in a good day's work. We're going to be done here. No more reaction at this point. It's not like everything just stops at that point. Okay? What's happening in every chemical reaction is, yes, you have reactants that are combining to form products, but the reverse reaction is always occurring as well. You have product molecules coming together to form your reactant again. So reactions are always going in both directions. And when it reaches equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So again, it's not like all reaction just magically stops at some point. It's just that every amount of reactant being converted to product is the same as products being converted back to reactants. Okay? So again, we got to update our way of looking at reactions here. These chemical equations, they're not just pointing in one direction. There's this balance going on, a back and forth going on. Okay? And this will continue until it reaches that equilibrium where everything remains constant. Again, it's not that the reaction stops, it's just that now the concentration of reactants and products are no longer changing. Okay? This sort of double-headed arrow here, and that was pretty sloppy, we can clean it up a little bit. This is a specific arrow that corresponds to like when we're talking about equilibrium here. Okay, so this is what we would call an equilibrium arrow. The lazy man's form that I default is like this as opposed to two stacked on top of each other, right? But we have this double-headed arrow to remind us that this reaction is going in both directions at the same time. Okay? Cool. So, these equilibriums, like when does a reaction reach equilibrium here? We can quantify that. And in fact, for every reaction that has been quantified using what's called an equilibrium constant. So let's talk about this. Okay? So for every chemical reaction, you can go and look them up in those big books that you see in lab, or of course nowadays everything's tabulated online in databases, but every chemical reaction has a unique equilibrium constant that we can look up, and that governs the amount of product and reactant that we should get once equilibrium is reached. Okay? So the one thing that you want to have in your mind for your equilibrium constants when you're building them, and this is something that I still chant to myself every time I'm building an equilibrium constant, is product over reactant. Okay, the ratio of the amount of product to reactant, that's what our equilibrium constant is telling us. Okay, so let's get our simple chemical equation here. And let's build the equilibrium constant for this here. Okay, so our K, and we're going to define this in terms of concentration. So we're going to put this little C, okay, is going to be the concentration of our product over the concentration of our reactant. Okay? So for our K's, we are going to remember products over reactant. This is the concentration of my product over the concentration of my reactant. Okay? Now, we balanced this chemical equation beforehand, and that stoichiometric coefficient is going to be important as well. When we're building our K's, our stoichiometric coefficient becomes an exponent. So this 2 in my balanced chemical equation is going to be a 2 as an exponent in my equilibrium expression. That 2 is on the product side, so I'm going to raise that concentration of my product to the power of 2. Right? So our coefficient in our balanced chemical equation becomes an exponent in our expression for K. Okay? So you could look up this reaction in a book and it's going to give you that the KC is like 2.5, let's say. That means that if you plug in the equilibrium concentrations, you will always get 2.5 for this reaction. And what's kind of magical about this is it doesn't matter if you start out with 0.1 molar in your flask or 100 molar in your flask, they will always reach the same equilibrium constant with regard to the ratio of their concentrations. Okay, so we'll work with this quantitatively here in a second. Let's make sure first that we can build this expression given a balanced chemical equation. All right, so I'm gonna put down a chemical equation and you guys are going to build me the equilibrium expression here. Okay? Don't forget, you're going to need to balance this chemical equation before you can build me the equilibrium expression. So how am I going to balance this? What do I need to put in there? A 2 on the product side. Cool. And then I'm going to remember products over reactants, right? So my product HI over my reactants. And now I have 2 reactants here. You're going to take the product of those 2 concentrations. It's going to be a multiplication. You will never see addition and subtraction in your equilibrium expression. It's always going to be the product of those concentrations. So the concentration of hydrogen gas times the concentration of iodine gas. And then the last thing I got to do to finish this off is remember that my coefficient needs to become an exponent in my equilibrium expression. All right, so I'm going to raise the power of that product, HI, to the power of 2. Okay? All right, so let's look at another one real quick. If we take aqueous sodium chloride and aqueous silver nitrate. Y'all talked about precipitation reactions in 1A. This one will form a precipitate, where I get solid silver chloride and aqueous sodium nitrate. Okay? But before we build our equilibrium expression, there's one more note that we want to make about how we construct this. Like we said, products over reactants. Let me make some room here. We said our stoichiometric coefficients become exponents. And the last thing that we want to know is that solids and liquids do not appear in our equilibrium expression. Okay, so one of the things that you may have noticed when I was doing my chemical equations here was I was being really good about putting the states of matter of those compounds as well. If it's a gas or if it's an aqueous compound, those we will see in our equilibrium expression. But if it's got that S for solid or that L for liquid, those do not appear in our equilibrium expression at all. Okay? And that's because they don't really have a concentration. If you have a solid there, its concentration is going to be remaining constant. It can't change because it's not a solution, it's not a gas. The number of moles in that little compact area is the same. Right? So when you build this equilibrium expression, you're going to follow the same rules that we talked about before, but you're not going to see silver chloride anywhere in that expression. Turns out that these reactions, these equilibriums, are independent of the amount of solid that you have. So again, I'm going to put my products over my reactants. But again, which one of these terms shouldn't be here in this equation? That concentration of silver chloride. So this we're going to exclude altogether. It just doesn't appear in that expression at all. Okay? All right, and then the last thing is that if your reaction involves gases, you can talk about gases in terms of the concentration of a gas, in terms of the number of moles you have per liter. But it turns out that a way more convenient way of measuring the amount of gas that gives you the same value, it's directly proportional, is pressure. So we can define our equilibrium constants in either concentration or in the pressure of these gases. And both are perfectly valid, right? It just depends on which one you're measuring here. So reactions with gases can have their equilibrium expression defined in pressure as well. And so this reaction here, the first one that we did, that involved only gases. So we could either give the Kc for that reaction in terms of concentration, or equivalently we could give the Kp, which we're going to follow the exact same rules, but now we're talking about the pressure of my product over the pressure of my reactant. And again, I'm going to raise that to the power of 2, right? My product concentration gets, my product pressure rather gets raised to the power of 2 because of that stoichiometric coefficient of 2 in my balanced chemical equation. What's up? You can mix and match, but it's way more convenient to stick with one or the other. But yeah, in theory, you can mix and match. It's fine if you had some solutions and some gases. Okay. All right, so now let's just build our equilibrium expression one more time. We're going to pick a slightly more complicated chemical equation, so you guys have to do some balancing here. Sorry. Okay, and you're going to build me my equilibrium expression. All right, is this thing balanced as is? No, what am I gonna have to do? I need a 2 in front of my sodium chloride, okay? Can I write a Kp expression for this reaction? No, I got no gases going on here, right? These are only aqueous solutions. The only way that we can talk about amounts of aqueous solutions are in terms of concentration, right? Molarity. So we're gonna write a Kc for this reaction. I'm going to do my products. Over my reactants. Okay, but what's wrong here? I got a solid in there. I can't have a solid in there, so we need to get rid of our calcium sulfate. And then the last thing I'm going to do to finish this off, I need to exponent, right? So my stoichiometric coefficient is going to be an exponent in my equilibrium expression. Okay? All right, so now let's use these sort of quantitatively here. We're going to go back to our simple chemical equation that we did at the beginning here, and then we'll complicate things. So, start off with this one, same one we were working with, dinitrogen tetraoxide being converted into 2 nitrogen dioxides. Okay. So we have a flask. That initially contains 2.0 atm of our reactant and no product. Okay, so we're going to kick this off with this flask that contains only 2.0 atm of our reactant and none of our product. All right, then our reaction is going to reach equilibrium. And the pressure of our N2O4 is equal to 1 atm. All right, so we've consumed some of our reactant, so the partial pressure of that reactant has gone down, and it's flatlined at 1 atm here. Okay, and so what we want to do is, what is the Kp for this reaction? We want to find that equilibrium constant for this reaction here, given this information. All right, let me make a little more room for myself. Okay, we have our balanced chemical equation. All right, we had our equilibrium expression. Our Kp is the concentration of the NO2. Oh, not concentration. What do I want? Pressure. The pressure of the NO2 squared over the pressure of the N2O4. So if I had my equilibrium pressures here, I could just plug them in and get my equilibrium constant. All right, I got one of them. Right, check, check. I have the equilibrium pressure of my reactant, but I'm missing this variable here. We got to figure out what the pressure of that nitrogen dioxide is at equilibrium. Okay, what we're going to do is a strategy that we're going to use over and over and over again in this course, and that's what's called an ice table. Okay, so I'm going to build this table. where on the left-hand side, I have my acronym, ICE. And then I'm going to have a column for my reactant. And a column for my product. All right, we're going to play this game over and over and over again in this course, building these ICE tables, right? So on the one hand, I have this acronym ICE. We'll talk about what that is on the left-hand side. And then I have a bunch of columns for each of my reactants and products. Okay? So the I in ICE stands for initial. Right? So how much of each of these do you start out with initially? In this case, we're talking about pressure, so I'm going to put the initial value for the pressure of each of these that I have at the very beginning of my experiment here. Right? So what's my initial pressure for my reactant, my N2O4? That's that 2.0. And what about for my product? How much of that do I have initially? 0, right? There's none of it in my flask to start out with. Right? So for I here, this is the initial concentration or pressure of your reactants and products. Okay? The C stands for change. So this is how these pressures are going to change as this reaction occurs and reaches equilibrium here. All right? So we're going to use the variable X in our change box here. Okay? The other thing that we have to remember is that what happens to the concentration of my reactant? Does it go up or down? All right, if this reaction's going on, is my pressure of my reactant going to increase or decrease as this reaction occurs? Reactants get consumed, right? So my reactant concentration or pressure is going to go down. So we're going to remember, we're going to use this variable X. Reactants decrease. Okay, so in my change box for my reactant, I'm going to put negative X. Okay, and then for my products, do they increase or decrease? Products increase, okay? So reactants decrease, whereas products increase. So in my product box for change, I'm going to put a plus X. Okay? But now if you remember, if we go back here, we looked at these very initial sort of lines here, and we said that the height of this red line here ended up being twice as big as our blue line here, because of that stoichiometric coefficient, right? For every molecule of reactant that gets consumed, I'm producing 2 molecules of product, okay? We have to account for that in our ICE table as well. So my product side rather, isn't just going to increase by X, it's going to increase by 2X, right? For every 1 molecule of reactant that I consume, I produce 2 molecules of product. So we're going to include that stoichiometric coefficient. Okay? So now the last box here, that last row rather, the E stands for equilibrium. right, in order for us to get what goes in this box in each column, we're just going to sum up our initial and our change boxes. Okay, so this is the sum of the I and the C boxes. Okay, so in that first column there, I'm going to have 2.0 minus x. And in my second column, I'm going to have 0 plus 2x, which is just 2x. Okay? So importantly, these are the pressures at equilibrium here. So I can substitute in for my equilibrium expression for my pressure of my reactant. I'm going to put in what's in my equilibrium box for my reactant. And for the pressure of my product, I'm going to plug in what I have in my equilibrium box for my product. Right? So we can redefine our equilibrium expression Kp this is now equal to 2.0 minus x. And this is a very common mistake algebraically that people make. That pressure of my product was squared, right? That 2x is squared. It's the whole 2x, not just the x. So I'm going to put in parentheses 2x squared, right? I need to hit that 2 and that x with that exponent. Don't just hit the x. That's a super common mistake that people make, right? Everything in that box gets hit with that exponent. Okay? So now if I can figure out what x is, I'm done and I can solve for my equilibrium expression. Okay? So in this particular problem, we just need to read back through our problem carefully. Okay? We are given the fact that at equilibrium, the pressure of my reactant, my N2O4, reaches 1 atm. Right? So, which one of these boxes here is equal to 1 atm? Which color? Right? At equilibrium, my reactant reaches a pressure of 1 atm. This is my pressure at equilibrium here. So this box here is equal to that 1 atm. So all I got to do in order to solve for x is say, okay, well 2.0 minus x equals 1.0, right? That's my equilibrium pressure. And we can take this and rearrange and solve for x. Everybody practice your algebra and solve for x. What? 2 minus what equals 1? Excellent. Okay? So we have x equal to 1. All right? Once we get to these ice tables, so I said we got to be good about our sig figs for our easy operations. As soon as we get to our ice tables, all of a sudden sig figs are going to go out the window because truthfully we don't have rules for exponents in sig figs. There's another set of rules that you would have to learn, and quite frankly they're going to stress that very highly in analytical chem. So I'm just going to kick the can down the road until you get then, and we're not going to worry about sig figs for these ice tables here. Okay? Now that I know the value of x, I can just turn around and plug all this into my equilibrium expression here. All right, so everybody take a second and solve it for me. Get my final Kp value here. Okay, so I'm going to go in and I'm going to substitute x is 1. So 2 times 1 squared over 2 minus 1. 4 over 1 gives me a value of 4 for my equilibrium expression. Okay? So these ice tables are going to be a really important way in which we go about solving these. These are going to work for even more complicated problems in the future here, right? We're sort of like laying this groundwork that we're going to build off throughout the semester. All right, so I'm going to give you all one to do on your own here. Let's look at a new chemical equation. All right, the initial concentration of my H2O is 2.15 molar. Concentration of my hydrogen and oxygen equals 0. Okay, so I'm going to start out with just some water vapor in this flask. All right, none of my product. And then at equilibrium, the concentration of my water vapor has decreased to 0.75 molar. Okay, so step by step here, what do we got to do? Whoa, Cartman, this guy sucks. I messed up on one of my lectures and my husband was roasting me, so I sent him that, yeah. All right. At equilibrium, first thing we got to do is balance. Then we got to find our expression for Kc. And then lastly, we got to build that ice table. Okay? And again, the building of the ice table is super important. That's something we're going to do over and over again throughout this course. So what I'm going to do is I'm going to give you guys a little bit of a head start, and then I'm going to sort of quietly start filling in up here so you can look up if you're getting stuck. All right, so let's fill in this ice table here. What am I going to put for my initial concentration of water? That 2.15. And what about my initial concentration for my products, hydrogen gas and oxygen gas? 0. Okay, for the change, I'm going to use that variable x. What's going to be the sign, positive or negative, in the water column? Negative, because it's a reactant. Reactants go down. And it's not just negative x, but negative 2x, because I got that coefficient of 2 out front in my balanced chemical equation. Okay. What about for my hydrogen gas column? What's the sign, positive or negative? Positive, because now I'm talking about a product. Product concentrations go up. So positive, and not just positive x, but positive 2x, because again, there's that coefficient of 2 in my balanced chemical equation for hydrogen. Oxygen is also a product, so that will be positive, but now there's no coefficient out front, so it's just going to be plus x. All right, then so for my E box, I just sum together the i's and the c's. So 2.15 minus 2x, 2x, and x. All right, so let's just swap these. So then I'm going to plug in, right? And just to be clear, I'm going to color code things here, right? My equilibrium concentration of water is that expression there in my equilibrium row. So that I'll replace right here. My hydrogen gas concentration is 2x. From my ice table, that'll go right here. And then finally my oxygen gas concentration, again from that equilibrium row. Okay, so plugging everything in, I get 2x, all of it squared, right? Make sure the 2 and the x are getting hit by that exponent, times x, all over 2.15 minus x, and that whole thing squared. What's up?
It's minus 2x.
Yes, it is. I was just making sure you were paying attention. Minus 2x squared. Okay, so again, just make sure that you see where I got these values from. Right? Again, the equilibrium box for water, that's what I punch in for my concentration of water. The equilibrium box for my hydrogen gas, that's what I punch in here. The equilibrium box for my oxygen gas, that's how I got that there. Okay? And then to go about solving for my value for x, I'm going to use the fact that at equilibrium, the concentration of water is 0.75 molar. So what does that correspond to in terms of these colored boxes here? The yellow, the green, or the orange? The yellow, right? The water at equilibrium is that 2.15 minus 2x. All right, so let's practice our basic algebra skills. Everybody take a second and solve for x for me. I said math was going to be kind of an important part of this course. This is about as bad as it gets here. We just need to remember our sort of basic algebra skills, right? How to rearrange equations to solve for x. All right, so we get that x is equal to 0.7. All right, so I'm done. No, right? So this is a very common problem is we kind of get lost turning numbers into more numbers doing our math, and we get to the end and we're like, all right, wonderful. Let's remember what the question is asking us though. It's not asking for x. We got to use that value, of course, but it wants the value for that Kc. So we got to plug this back into our Kc expression here. All right, so in what is Kc? We're just going to substitute 2 times 0.7 squared times 0.7 over 2.15 minus 2 times 0.7 squared, right? Just plug in that value for x back into our equilibrium expression, punch it all into our calculator. All right, and if you get everything in there correctly, you would get that x has that Kc has a value of 2.44. Okay. We are at this point now, especially with these ICE tables, we're using a little bit more advanced algebra here. We got exponents going on in there. There is very much so rules for carrying sig figs that you will learn when you get to analytical chemistry, and I'm just going to go ahead and kick that can down the road for you to learn that then, all right? So at this point here, when we're doing our ICE tables, our algebra is a little bit too complicated. We're not going to worry about our sig figs here. All right, so give it to me to 2 decimal places. Cool. So I asked you for the value of Kc here, right? What if instead I said, what is the concentration of H2 at equilibrium? How in the heck am I going to go about getting that? Yeah, right? So where on my ICE table is the concentration of hydrogen gas at equilibrium? Yellow, green, or orange? The green. That's what that expression is, right? That's the concentration of hydrogen gas at equilibrium. So if I'm asked for the concentration of hydrogen gas at equilibrium, I'm going to use that expression there. I already got what x is, right? So the concentration of H2 at equilibrium is just 2 times x, or 1.4. Okay, since I'm talking about concentration, what should be my units? Big M, molarity, right? That's what I was given at the start of my problem here. Okay, and we could have just as easily have done this if you were given pressure values at the beginning. Remember, gaseous reactions, we can talk about it either way, right? So if you're given concentrations, you'll do a Kc. If you're given pressures, you'll do a Kp, right? The procedure for solving for them is identical. All right, and then I guess last thing I could ask you about this reaction, does this reaction, which direction does this reaction favor? Products or reactants? The products, right? How do we know that? Because that value of K is greater than 1. Does it strongly favor the products, or am I in that dynamic equilibrium range? I'm less than 10 to the 3, right? Less than 1,000, so I'm still very much so in that dynamic equilibrium range. And you can kind of convince yourself of that punching in numbers here. You have a good amount of both reactant and product at equilibrium. So in this particular problem, we're going to be given a chemical equation. All right, this is going to make formaldehyde. All right, so like always, we're going to be given this chemical equation, not necessarily balanced. All right. And I'm going to tell you that the initial pressure of both reactants is equal to 3.42 atm. Okay, and I'm going to tell you that the Kp for this reaction is 0.763. And I want to know what is the pressure of that product at equilibrium. Right? So in this particular problem, I'm not asking you for it to solve for that equilibrium constant. I'm giving you the value of the equilibrium constant, and we're going to use that to figure out what our concentrations are, in this case our pressures are, at equilibrium. All right, so we're going to do it the same way, starting out here. You're going to balance. You're going to build that equilibrium expression for Kp. And then lastly, set up your ice table, just as we did before. All right, so like before, I'm going to give you a little bit of a head start. All right, and then we'll go in and work on it together. Okay, so I got my chemical equation balanced. I built that Kp expression here, products over reactants, and making sure that my coefficient became an exponent. I'm filling in my ice table here with my initial pressure of each substance. It says that my two reactants have an initial pressure of 3.42 atm, so I got that for both of those boxes. When I do my change, what's going to go in my change box for my C2H4? What's going to be the sign? Negative, because it's a reactant, right? And there's no coefficient out front, so this will just be negative X. What about for the oxygen, positive or negative? So this is also going to be negative because oxygen's also a reactant here, right? Reactants get consumed, they go down. And then my CH2O, positive and positive 2x because of my coefficient out front here. All right, so then I'm going to sum everything up. 3.42 minus x, 3.42 minus x, and then 2x. Okay, and now that I have my ice table built, I can fill in for my equilibrium expression the pressure of my product at equilibrium, that's that 2x. The pressure of my O2 is the 3.42 minus x. And same for the pressure of the C2H4. So plugging everything in, 2x squared over, all right, so 3.42 minus x times 3.42 minus x, right? I can condense this to 3.42 minus x squared. Okay? Now, unlike before, I'm not asked for the value of Kp. That's not what I'm solving for. I was actually given that value of Kp. Right? So I know that this expression here is equal to that 0.763. All right, so this is my algebra problem here. All right, and there's one very, very helpful rule from algebra that we want to remember here. If we take a squared divided by b squared, that's the same thing as a divided by b all squared, right? So I can pull out that exponent. So we're going to need to do that in order to simplify things. This is going to become 2x over 3.42 minus x, all of it squared, equals that 0.763. All right, so everybody take a second, practice your algebra skills here. Solve for x. All right, how am I going to get rid of that exponent? I need to just take the square root. And you can do anything you want in algebra as long as you do it to both sides. All right? So in order to get rid of that square root, or in order to get rid of that exponent, I'm going to take the square root of both sides. All right, and then just to give you a hint, you got x on top, x on the bottom. You got to get them together, right? So move that denominator to the other side of your equation. All right, so fun with algebra here. I want that denominator gone, so I'm going to multiply both sides by 3.42 minus x. All right, and why am I doing that? Because on this side, on my left, it'll cancel out. All right, so let's just simplify. Okay, I got x on one side, x on the other. I need them together. All right, they're stuck in those parentheses. So I'm going to distribute that square root of 0.763 inside those parentheses. So square root of 0.763 times 3.42 minus the square root of 0.763x equals 2x. All right, I'm going to distribute that. I got to get rid of those parentheses. So I'm going to distribute that value inside of those parentheses. Okay, and how am I going to get my x's to the same side? Somebody said it. Add it, right? I got to add that term to both sides. So now to both sides, I'm going to add square root of 0.763x. So now I have 2x plus the square root of 0.763x equals some number. Square root of 0.763 times 3.42. All right, I got x in both of these terms, so what can I do? We can pull it out. We can undistribute that x, right? So this is the same thing as x times 2 plus the square root of 0.763. All right, I had x in both of these terms, so I just pulled it out. And then finally, to get x all by itself, I'm going to divide both sides by that 2 plus my square root. So at the end of the day, these will cancel out, and I'll be with x equals whatever the crap this number is. All right, so again, math is a very important part of the course. We're not doing any multivariable calculus or anything crazy like that, but we do have some pretty serious algebra that we're going to be doing. We need to be comfortable rearranging equations in order to solve for our value of x. Like I said, I wanted to do this one specifically because this is about as bad as it gets here. All right? So, punching all this into my calculator. I get x equals 1.03962, blah, blah, blah. And I'm done. Or am I? No, because what was I being asked for, right? Remember, you're going to get to all the end of this math and you're like, nice, I'm out of here. But what was the problem actually asking me for? I want to know what the pressure of that product is at equilibrium, and where is that on my ice table? Is it the yellow, the green, or the orange? The orange. So I have to remember to go back to that ice table. I'm not asking for the value of x. In this case, I'm asking for 2x. Okay? So 2 times that value. We'll just cut it off at 2 decimal places here. So my pressure of my CH2O at equilibrium is 2.08. ATM. All right, now I get done with all this algebra. I solve for x, and I'm like, oh man, I got no clue if that went well or not. I have no idea if I actually got the right answer. How can I check? How can I check to make sure that that value for x is correct? If I plug it in to my equilibrium expression here, I better get that same value that's given, right? So if you're gonna, at the other end of all that dark algebra tunnel, you're like, oh crap, did that go well or not? Plug it back into your equilibrium expression and check. You should get that same value back. Okay? Cool. Now we're going to introduce what's called the reaction quotient. Okay. We use this uppercase Q for our reaction quotient. So let's just take our simple example that we've been using. Okay. The expression for my reaction quotient Q is literally the exact same as an equilibrium expression, right? So for this particular reaction here, let's do it in terms of concentration. It's my concentration of products over my concentration of reactants, right? It's just that same equilibrium expression. Okay, so what's the difference? We call it K if the concentrations that we're punching in are at equilibrium, right? K is a constant value. It's not a variable. So the only way that K works is if the numbers that I punch in there are my concentrations at equilibrium. Then we call it K. If we're punching in values anywhere else outside of equilibrium, we call it Q. Okay, so Q is just our equilibrium expression outside of equilibrium. All right. So why is this helpful? Okay. Previously, in a previous problem, and to be perfectly honest, I made this up, but we're just going to roll with that number. We said that this reaction, our Kc, or actually it was a Kp that we solved for, was equal to 4, right? So now let's say that, all right, great. I did that reaction. I let it go to equilibrium. Now I'm going to come up to a brand new flask here. And this flask contains 3.75 ATM of that reactant, the N2O4, and 1.65 ATM of the product, nitrogen dioxide. All right, and I want to know which direction this reaction is going to go. This is not necessarily at equilibrium. I want to know if more product's going to be formed or if the reaction is going to go in the reverse direction and start forming reactants instead. Okay, that's why our value for Q is going to be very helpful. So let's solve for our value of Q just by punching in, I guess we should have done KPs, pressure of NO2 squared, pressure of N2O4. All right, let's just go ahead and plug our values in here. We are outside of equilibrium. Take this to a new page. So I'm going to take my 1.65 and square it and divide it by the 3.75. And I get this value for Q of 0.726. Okay? So what does this do for me? If our value for Q is greater than that of K, this will shift towards the reactant side. If my value for Q is less than K, this will shift towards the product side. So based on my Kp value of 4 and my value for Q of 0.726, am I going to shift this? Is this reaction going to continue in favor of the products, or is it instead going to go in the reverse direction towards the reactants? My value for Q is less than that of K. Right? So this one will just continue to react towards the product side here. Okay? So the idea of this reaction quotient, it is just your equilibrium expression. There's no different way that you build it. The difference is that you're plugging in values outside of equilibrium, right? The K expression only works if what you plug in is equilibrium values. And the reason that we do that is then we can compare and say, all right, if that Q value is greater than K, my reaction is going to be moving in the reverse direction. If my Q value is less than K, it's going to be moving in the forward direction.